Hello everyone, my name is Marduhi Petrosian, and today I'll be discussing our CTD method to connect the dots and interpret complex networks, as well as its application in the Playbook. I would first of all like to thank the ERCC-DCC, the Common Fund Data Ecosystem, Links, String, and XRNA. CTD can be used to connect the dots and identify highly connected sets within complex graphs. CTD can be applied to many different types of biological networks to identify informative subsets of, for example, genes, proteins, or metabolites. Because CTD is a generic method, users that could benefit from the application of CTD on the Playbook are any scientists that have a complex dataset that can be represented as a graph. I would first like to discuss some CTD use cases. So in this initial use case, we showed that CTD was able to identify biomarkers of response to chemotherapy in breast cancer. CTD identified highly connected sets of nodes, which we then showed were associated with response of the breast cancer samples to chemotherapy agents. We then showed that the small sets of genes identified by CTD were predictive in determining the best response for murine models of breast cancer. CTD has also previously been used to interpret metabolomic modular perturbations and to help screen patients for inborn errors of metabolism. CTD could also be used to expand the list of GWAS hits. While GWAS may be underpowered to identify all informative genes for rare diseases, CTD could be used to expand this list by identifying genes that link highly connected GWAS hits and may therefore be guilty by association. CTD has been deployed as a tool on the Playbook Workflow Builder. The Workflow Builder application allows users to build complex workflows with many different types of tools. By deploying CTD on the Playbook, we hope to make it more accessible to a general audience of users. With the Playbook integration, you would first select a set of genes that you are interested in. You can then go into the following cards and select Perform CTD with gene set using String. String is going to be our protein-protein interaction graph that we are querying our genes against. So say you're interested in genes A, B, C, and D. Once you've selected the Perform String card, you would then identify which genes in your set are going to be highly connected, in our case, A, B, and C. What performing CTD also allows you to do is to identify genes that are guilty by association. So in this case, the gene that's highlighted in red in the middle here. You would also get as an output a JSON graph that highlights all of the genes of interest as well as those that are guilty by association. So if you press the plus button here, you can see that you can extract these CTD graph nodes. And what this allows you to do is plot out as a network all of the highly connected sets of genes, as well as the genes that are guilty by association. So you can also choose to extract just the guilty by association genes, which would list them here, or just the highly connected sets of genes, which would create a list such as the one you see here. The question we would then like to ask is, how can CTD be used to address biological questions? So first of all, network modeling can be used to identify and visualize relationships in highly complex datasets. So in this example here, we're looking at the gene expression differences between mice with triple-negative breast cancer that were treated with a control versus chemotherapy agent. So one of the questions with datasets such as this is, how can you identify the biological signal within the heterogeneous graphs? Multi-omic datasets can generate vast amounts of data, but how can this data be interpreted? And more pertinently, which nodes, genes, proteins, or metabolites are linked to your phenotype of interest? Within these complex networks, CTD can be used to identify small, informative subsets of genes. There are other network methods, such as weighted correlation network analysis, or WGCNA, which can be used to identify graph clusters. However, these methods tend to cut all of the modules at the same height, and then use these modules to correlate to the phenotypes of interest. But the problem here is that these modules are often too large to be biologically tractable, and that by using module eigengenes to correlate the modules to the phenotype of interest, it may flatten the signal and could overlook informative genes. CTD circumvents these problems by identifying highly connected significant sets of nodes within complex weighted graphs. Say you're interested in the nodes of interest on the left, which are in gray and purple. You can query their connectedness using CTD in the weighted graph in the middle. So CTD will identify that the nodes in purple are highly connected, and it'll also assign an upper limit p-value to the set of nodes. CTD does this using relative patterns of connectedness, data compression, and the algorithmic significance theorem. One of the advantages of CTD is that it allows us to calculate the p-values of highly connected sets without using computationally costly permutation testing. And CTD does this by allowing us to compare the actual encoding length, or how concisely a set of nodes may be encoded, versus the null encoding length. This allows us to calculate a p-value for each set of nodes. So for example, if we're starting with this graph and the set of nodes A, B, and C, we see that there's many ways to get subsets of 2, A to B, A to C through B, and B to C. There's also one subset of the length of 3. If we want to compare the actual versus null encoding length for the subset of length of 3, so A to B to C, we can first calculate the actual encoding length, which would be a combination of how many bits it takes to encode A, in this case 3, and then how many additional bits it'll take to encode the path from A to B and B to C, so 2. We compare this to the null encoding length, which is going to be the log 2 of the combination of 9 and 3, which would be 6.39. So if you take the null encoding length and subtract the actual encoding length, you'll see you have a difference of 1.39 bits. So therefore, you can calculate the p-value as 2 to the negative 1.39. So the p-value for this set of nodes would be 0.40. While this is insignificant, this is the way that CTD calculates the p-value for each set of nodes in a weighted graph. In summary, CTD is a method to connect the dots, and we've just discussed how this method works without computationally costly permutation testing. CTD can be used to identify small, potentially biologically informative sets of nodes within many types of weighted graphs. And CTD can be used to address many different types of biological questions. We hope that you'll find the integration of CTD with the Playbook to be a useful tool when analyzing your own complex datasets.